Hello everyone. In this video we are going to talk about reduced row echelon form. So first let's recall what we mean by row echelon form before we add the reduced to it. Right, so row echelon form for a matrix or for a linear system, since you can still think of them having rows, means all rows with only zero entries or zero coefficients, if you're thinking the system, are at the bottom, and every pivot or leading coefficient in a non-zero row is to the right of the pivot in the row above. And of course, the top row, that's not going to be the case, but for every row below that. And as we have seen thus far, row echelon form makes back substituting and solving for our linear systems much easier and quicker. And we will see that we won't have to do any of this back substitution once we learn about reduced row echelon form. So we're about to define reduced row echelon form. I'll often abbreviate this RREF. And its definition is as follows. So we say a matrix is in reduced row echelon form if it satisfies these three conditions. So first, it's in row echelon form. And then the reduction is that first we make every pivot entry or leading coefficient 1. And after doing so, we ensure that each column containing a pivot has that 1, and then every other entry in that column is 0. So now let's go ahead and take a look at several examples and determine which ones are in row echelon form, reduced row echelon form, or maybe neither. All right, so let's go ahead and look at each of these in turn. So if we look at the top left here, this one should pretty clearly be not in either, right? So we would want to switch these because we see pivot here, and then this one should be to the right of the one above it, but it's to the right of the one below it, right? So this is not in echelon nor reduced row echelon form. So the one after that. Okay, so again, we want to identify our pivots, right? So we see these. The all 0 row is last. So this is definitely an echelon form, right? So the issue is this, right? So we look at a pivot column. These are all 0. That's fine. But this guy here is not 0, and so that's a problem, right? We would want to eliminate that 1 and make it 0 above the pivot in row 2 and column 3, okay? So this is just regular old row echelon form. Okay, so for the bottom left, all right, we again have 2 pivots, and we have the same issue, right? Something above that second pivot. So this is also row echelon. Now the one after that, we're fine, right? So even though we have this 3 up here above, well, it's not in a pivot column, so we don't really care, right? We have the 0 and 0 here, we have the 0 and 0 here, and so this one is in reduced row echelon form. And the last one is another one that is neither, right? Okay, so for your first exercise, I want you for these 4 matrices to just write down whether it is in row echelon form or REF, reduced row echelon form, or neither. So now we're going to look at Gauss-Jordan reduction, so named after Carl Friedrich Gauss, a German mathematician, and Camille Jordan, a French mathematician, but we're horrible Americans here, and so we'll just say Jordan. So this is just the process of reducing to reduced row echelon form. Okay, so right, we call getting to row echelon form Gaussian elimination, or Gauss's method, and then this is Gauss-Jordan reduction. All right, so we're actually going to start from the linear system itself here. So with this one, right, we turn it first into an augmented matrix. And so with this 2x2 system, it shouldn't be too bad. We are very fortunate to already have a 1 in the pivot position here. So we'll first subtract 4 times the first row from the second row. So that results in this matrix. And then again, in the original Gaussian elimination, right, we're already done. This is in row echelon form, and we could of course back substitute and solve, but here we want to make this pivot 1, and so we're going to multiply by negative 1/7 here. We then get this matrix, and the last thing that we have to do is, right, this is a pivot, and so this must be made a 0. And so we are going to subtract the second row from the first row. We want to do this after we, get a 0 below our initial pivot up here. That way we don't change the first column. And so this is going to be our last step, right? So we'll now have 1, 0, 0, 1, and then we have negative 1 minus negative 1, which is 0. And so what do we end up with? Well, this is great, right? We have 2 pivots, but because we have zeros there, we can actually just read off the solution, right? So x1 is 0 and x2 is negative 1, or writing it in column vector form, 0, negative 1. So now let's do a little bit more involved example. So first of all, let's note that we have all zeros over here, and so we know that this is a homogeneous system, and therefore this is going to have a solution. So we know this is going to be consistent. So let's go ahead and put it in augmented matrix form. And so again, we have a 1 as our first pivot, which is very nice. So we're going to be able to really eliminate everything below that right away. So we'll do that in just one step here. So 2 times row 1 will subtract from row 2, and just subtract row 1 from row 3 as well. So that results in this matrix, and we'll then look at the next pivot, right? We want this to be 1, so we'll go ahead and make it 1. We'll multiply by negative 1 here. All right, so we get a 1, 3, 1 there, our favorite zone defense. And now that we have that 1 in the pivot, we're happy about that, and so we'll want to get rid of this negative 3 below it, right? So we can add 3 times row 2. And now we are at least in echelon form. So we have 3 pivots in this case, right? And that means that x4 is going to be a free variable, right? But we want to do a couple of things here. One, we want to make this into a 1 and not a 9, and then we'll want to start eliminating above pivots in their columns. So first I'll make this a 1, so we'll just multiply by 1/9 here. All right, and so it's best to work kind of right to left as you go back up from the bottom. And so we'll look at this pivot and eliminate above. So we'll go ahead and do minus 3 times row 3 here and minus row 3 here. Okay, so now we have this system, and finally we just want to eliminate above the second pivot, deal with this 1, and we'll be done, right? So the non-zero entries in the last column, that's perfectly fine because that's not a pivot column at all. So here we'll just subtract row 2 from row 1, and we get this. And this is good practice because now we can, again, find our solution set. So again, x4 is free, right? And so we have x3 is equal to negative 1/3 x4. X2 is going to be 0, and x1 is going to be negative 2/3 x4. And so our final solution, I want to write it out, is going to look like this, right? We have our 1 free variable, and we can write everything else in terms of it, and of course x2 is just 0. And for your second exercise, I want you to take this system and use Gauss-Jordan reduction to put it in reduced row echelon form, and then use that to write down your solution set using column vector notation. Thank you for watching.